Hi. So in this lecture, I'm going to switch gears quite a bit and start talking about current in a conducting matter. Um, so pretty much the fundamental starting point of the discussion of a current flow in a conducting matter is this equation shown right here, J equal to sigma E. And for those of you who are not already familiar with this is in fact a more microscopic way of expressing what's known as the Ohm's law. Okay, Ohm's law is a circuit law, as many people think, saying that the total current through the wire is proportional to the voltage applied, and the relative ratio of the current divided by the voltage is known as the resistance, which is a characteristic of any given material. However, from a more microscopic perspective, the circuit version of Ohm's law, V equal to IR, is actually just a consequence of this more microscopic relation expressing the current density, which is a vector, as a quantity being proportional to the electric field with some constant that is typically called the conductivity or electrical conductivity. Okay, so if you want to sound like a professional, then at least professional physicist, then when you talk about Ohm's law, you should really be writing down this relation rather than the V equal to IR on a piece of blackboard to impress your friends or non-physicists. Okay, so now the thing that stands out immediately from this relation is that in order for the current to exist inside a conductor, then you must allow for the existence of at least a small amount of electric field in the conductor. Otherwise, this relation would not be able to produce any current. And I'm emphasizing this because probably you remember from my earlier lecture that in a equilibrium situation, you cannot allow any kind of electric field inside a conductor because any finite electric field inside a conductor would immediately imply the motion of electrons. And if you recall that argument, in fact, I used this very relation in order to argue just that point. So what's happening is that when you apply an electric field and some current flows through the wire, then while the current is flowing, there's a small but some finite amount of electric field which penetrates well inside the conductor. Okay, so that's the first thing I wanted to emphasize. And the other thing is that this relation suggests a linear relationship between the amount of current and the amount of electric field. And although this is an empirical law, there's in a way there's nothing fundamental about this relationship. But empirically, it turns out that in pretty much all kinds of metals that you encounter, this relationship holds almost perfectly. And so, in a way, this is a kind of a universal law, at least as far as the metallic systems are concerned. Okay. So Ohm's law, at least for metals, is I would say it's the fundamental law governing the behavior of a metal, and it's extremely difficult to find an exception to that. Okay, so Ohm's law was discovered around 1810, 1820, if I remember correctly. And as far as we know, the first correct explanation of Ohm's law, uh, the theoretical explanation, was given around the year 1900. So that's almost 80 or 90 years after the discovery of Ohm's law. And I think the reason why it took so long for people to come up with this theoretical explanation was that it took people quite a while to accept the existence of some sort of particle-like object that flows inside a conductor which carries the charge. And once you accept the existence of some charged particles that flows down the metallic wire and carries the current, then it's pretty easy to write down some equations to explain its behavior. But the main trouble was that because these charge carriers were basically electrons, and electrons are so small that there's no way you can see them with bare eyes. So it took scientists quite some time to fully embrace the existence of these small charged particles. And as you probably know, it's through Thomson's experiment at the very last years of the 19th century, Thomson's cathode ray experiment that finally convinced people that there are these little charged particles called electrons. And I believe this approach by Drude was proposed just a couple of years after Thomson's announcement for the discovery of electrons was made. Okay, so let's examine what exactly is the model set up by Drude to explain the Ohm's law. So as a matter of fact, this model by Drude is embarrassingly simple. This is nothing but the idea is nothing but just that of adding a frictional force to the Newtonian equation of motion. So you have this m times the acceleration, where m is the mass of the charge carrier, which we now know to be the electron. And that's equal to the force according to Newton's second law. And for electrons, that force is coming from the electric field. So it's just the charge of the electron multiplied by the electric field. And the other thing I want to emphasize in this equation is that the very notion of electric field was not really established until after the work of people like Faraday and Maxwell and so on, which took place around 1830s and 40s. So so that was another piece of ingredient which was not immediately available at the time of Ohm's discovery. And now the key improvement made by Drude is the addition of this term right here, which, if you have studied classical mechanics, you will immediately recognize as the velocity-dependent friction force. Okay, so that's really the only thing that Drude did as a matter of innovation. And as we all know very well from studies of classical mechanics, uh, you can reach what's known as the steady state. That is the situation where this frictional force balances out the external force, so that the particle stops accelerating but maintains a constant speed. So this steady state condition, in the case of this equation, leads to the velocity that is proportional to the electric field, with a constant of proportionality given by this combination of electric charge, some time constant called the scattering time or relaxation time, and divided by the mass of the charge carrier. And all told, this combination is called the drift velocity. And drift velocity is basically the same concept as the terminal velocity in the motion of a object in the presence of damping in classical mechanics. Okay, so now with this expression for the drift velocity, we can write down the expression for the current density explicitly, because current density is nothing but the charge density, where I've written the n for the number density. So to convert the number density to the charge density, one needs to multiply it by the charge of an electron, which is minus E. So now if you combine all of these things together, then it's number density of electrons multiplied by the electric charge squared times the relaxation time divided by the electron mass. And all of that is multiplying the electric field. And therefore, you have established a linear relationship between the electric field and the current density with the proportionality constant given by this particular combination of numbers. And that's called the electrical conductivity, or just conductivity for short. Okay, so according to Drude, this conductivity is proportional to the number density of electrons, inversely proportional to the mass of the electron, and proportional to this mysterious new quantity called the relaxation time. Okay, so Drude did this calculation and proposed his theory around the year 1900. That's more than 20 years, more like 25 years before the final discovery of quantum mechanics and Schrödinger's equation. So obviously, Drude knew nothing about quantum nature of the electrons. So once the quantum mechanics was discovered, this entire scheme that Drude laid out in year 1900 had to be revisited and presumably revised. And of course, people did that once they understood enough about quantum mechanics and how to do many-body quantum calculation. And interestingly, after all that sophisticated calculation is performed successfully, people kind of get back to exactly the same expression as Drude had obtained several decades earlier. So so drew this expression for the electrical conductivity is one of those examples where somebody got the right answer very early on, but not necessarily for the right reason. But somehow his effort was met with quite a bit of good fortune that the answer remained correct even after the more sophisticated and correct calculations have been performed much later. Okay, so it's even conceivable to extend this Ohm's relation to the case of inhomogeneous conductivity. So by inhomogeneous, I mean this conductivity value can change from place to place. And most metals and most materials, for that matter, are not completely homogeneous. So it's entirely conceivable that on the scale of several nanometers, for example, you do have a appreciable variation of the electrical conductivity. And to accommodate such a situation, it would be wise to allow for the spatial dependence of the electrical conductivity. And why stop there? Just you can also start allowing for the spatial dependence of the electric field as well, which makes the current density itself to be a space-dependent quantity. Okay, so but even after this relaxation of the conditions, uh, there's no way you can relax this condition. Okay, because this divergence of the current density equal to zero, this reflects a more fundamental constraint, namely, it reflects the principle of charge conservation. And the charge conservation led to the existence of the continuity equation. And once you assume the time independent situation, then the continuity equation just reduces to this divergenceless condition for the current density vector. So this is a very strong constraint that should be applicable even in the inhomogeneous situation. Okay, so one can try and put these two equations together, divergence of the current density equal to zero and the current density equal to some local conductivity multiplying the local electric field. Then this divergence thing breaks down into two separate terms, uh, this one and this one. Uh, but uh, but what shows up here is the divergence of the electric field, which we know from Maxwell's equation, or one of Maxwell's equations, to be related to the local charge density. Okay, so now combining this equation with this previous equation, you can express this divergenceless condition in this rather differently looking form. Okay, so on this side of the equation, you have the product of the local electrical conductivity multiplying the local charge density. Now, however, if the whole system was homogeneous, and therefore this conductivity did not have any special variation, then the left-hand side vanishes, which would mean that the right-hand side will also have to vanish. Okay, and Now, what's the meaning of that? Well, actually, what it means is that in a completely uniform wire, there can be a current flow, but this current flow is not accompanied by any sort of charge disturbance or charge inhomogeneity. So what I mean is that if there were any charge inhomogeneities, then it's possible to create locally some regions where the net charge is not zero, but maybe you have a lump of region with an excess positive charge and you have another lump with an excess negative charge, but such situation can never arise once you assume a uniform medium where the conductivity remains constant everywhere. Okay, and as another consequence of that, if the net charge remains zero, if the net charge density remains zero, then according to Maxwell's equation, that means that the divergence of the electric field also has to remain zero. Now, so what that implies is if there is a current flow inside a conductor, that would inevitably imply that some electric field has to exist. But this electric field can only exist in a manner which is consistent with this equation saying that the divergence of that electric field has to be zero. Okay, so the electric field can exist inside conductor and therefore drive some current through the conductor. However, they can only exist in a manner which is divergence free. Okay, so that's another quite broad consequence of the simple manipulations that we performed with both Maxwell's equations and the continuity equations and the Ohm's law, J equal to sigma E. Okay, so I like seeing these sort of important consequences being inferred from a very simple consideration and almost trivial looking manipulations of equations. And that's kind of the beauty of doing theoretical physics, that you can derive important statements on the basis of very simple calculations. Okay, so now let me touch upon another important theme that permeates the physics of a conductor, current carrying conductor, and that is the issue of Joule heating. Okay, so this Ohm's law, J equal to the conductivity multiplying the electric field, is fundamentally a consequence of some inelastic collision. So this is a pretty big statement, so I probably have to break it down to a couple of simpler ingredients. First of all, inelastic collision means the following. Earlier in the drew the theory, we wrote down this very simple equation and introduced this constant tau. And I just introduced it as a relaxation time, but never really explained what is the microscopic source of such a relaxation time. Okay, so in a couple of words, this relaxation time tau arises as a consequence of the following processes. Imagine an electron running down the running down the metallic wire. Obviously, it saves a lot of other electrons, and there are also other atoms, whole bunch of atoms that the electron has to pass through. So it will experience a whole bunch of collisions while it tries to travel down the wire. And as the electron collides with other particles or other objects, it will exchange energy with them. And some of these collisions will be elastic, meaning that the electron energy remains the same both before and after the collision. However, inevitably there will be processes where after the collision, the electron will have lost some of its energy. And that sort of collision is known as the inelastic collision. And such inelastic collisions are the source of this relaxation time tau. Okay, let me try to justify that statement by a number of other arguments. Well, one argument is the following. You can invoke something called the time reversal operation, which is a common operation in thinking about physical processes. So formally, time reversal means you change t to a minus t. Or using a movie analogy, instead of running the movie forward in time, you will be running it backward in time. So when you see a movie running backward, a current that flows in one direction would now seem to flow in the other direction, meaning that the current density vector J would have become a minus J. Okay. However, the electric field direction depends entirely on the location of the charges, because charges are the source of the electric field. And even if you run the film backwards in time, you're not going to see the charges being located at different positions. So therefore, the electric field will not change sign at all under the time reversal operation. Okay, and this conductivity, electrical conductivity, is some number associated with a given material. So as such, this is just a scalar which will remain the same scalar under the time reversal operation. Okay, just running a movie backward in time will not make will not be able to change the sign of the conductivity. In fact, that's actually doesn't make any sense, because conductivity by definition can only be a positive number. Okay, so what does that mean? Well, under the time reversal operation, this expression on the left this expression on the left changes sign from J to minus J, but both of these expressions, the conductivity and the electric field, they don't change the sign. Okay, so under the time reversal operation, these equations will look like J equal to minus sigma E. Okay, so now it seems like this equation is kind of paradoxical or even wrong, because in one coordinate frame where time flows forward in time, you have a J equal to sigma E, but in another coordinate frame where time flows backward in time, then you have J equals to minus sigma E. So which equation is correct? You might wonder. And the answer is that the Ohm's law is a kind of law that breaks the time reversal symmetry explicitly. Okay, so once you write down the Ohm's law, then it's completely illegal to try to reverse the direction of time, which means you are simply not allowed to use the time reversal operation to write this relation as J equal to minus sigma E. Okay, and energy dissipation, processes that dissipate energy typically do that. They break the time reversal symmetry. Okay, because if you observe something in the forward direction in time, then the process seems to lose energy. But if you run it backwards, then the process seems to gain some energy. Okay, so the processes look quite different depending on which direction you choose to move the time on. Okay, so basically, I guess what I'm trying to say is that physical processes which do not conserve the total energy, if you write down equations describing such energy non-conserving processes, then these equations tend to break the time reversal symmetry. And Ohm's law is just one famous example of that relation, that sort of relation which violates the time reversal symmetry in an explicit manner. Okay, so now let me try a more straightforward explanation of the fact that there is an energy dissipation process going on with the Drude equation. So you write down this Drude equation, and then on the basis of this equation, you work out the time derivative of the kinetic energy, 1/2 mv squared. So this expression is equal to Drude law once you multiply both sides of the equation with the velocity vector. Just take the inner product. Okay, then this right-hand side will be turned into this expression. However, noting that the v is just the time derivative of the position vector, dr dt. You can actually convert this expression as the time derivative of the potential. So what you end up having is the time evolution of the total energy. So here's the kinetic energy, and here's the potential energy. You add them together, and you get the total energy. So the rate of change of the total energy is not zero anymore, but it's some constant multiplying the velocity square, which is always a positive quantity. And the important thing is that there's a minus sign over here, which guarantees that you only move the system, you only evolve the system in a way that will decrease the total energy at all times. And that's a phenomena in which energy gets dissipated. All right. So in this seemingly simple process in which electric field drives the electrons and creates a current flow, what happens is that the electric field obviously continues to do work on the electrons because electrons move in the direction that's parallel to the electric field, and therefore the motion is taking place along the direction of the electric force. And when the direction of motion is parallel to the direction of the force, you know from fundamental theories of classical mechanics that there's work being done on that particle. So obviously, electric field continues to do work on the electrons, but the usual work energy theorem would expect you to believe that then that work will be converted into the increase of the total energy of the electron. However, the electron kinetic energy fails to increase continuously, as we know, because after some time, the electron will have achieved a steady state, always traveling at the same drift velocity and not increasing its speed beyond that. So you keep doing work on the electrons using the electric field, but somehow all that work is not being converted into the increased kinetic energy of the electron. So that means the energy is somehow being wasted. But that sentiment is precisely what's expressed and what's captured by the first law of thermodynamics, right? So when you do a work on the system, and it's entirely possible that that work is converted all into the heat produced by the system. Okay, so the fact that you're always doing some work on the electrons, and yet the electrons are not picking up any more kinetic energy, implies that there is a heat generation by the current carrying wire, which exactly equals the amount of work being done on the electrons as the electric field drives the electrons forward in the direction of the field. Well, using that principle of thermodynamics, we can actually calculate how much heat is being generated by the wire as it transports some electrons across its body. Well, we don't know how to compute the heat, but we do know how to compute the work being done on the carriers. Okay, because that's a mechanical piece of calculation. So just brush up your old knowledge of classical mechanics, which will tell you that the rate of change of work, that's also called power, the power equals the force times the velocity. To be more precise, it equals the inner product of the two vectors, and one needs to sum that inner product over all the electrons because there are many electrons in the wire. And this force is the electric force is in origin, so this is equal to the charge of the electron multiplied by the electric field. Now you take that inner product with the velocity of the individual electron. But this sum can be converted to an integral of the inner product of the current density vector with the electric field, and then integrated over the entire volume of the current carrying wire. So if you successfully manage to compute this integral, then what you obtain is the rate of heat production by the wire as it carries the current. Okay. Now we're going to do some more manipulation of this integral. Notice that this inner product can be converted to the inner product of the current density vector with the gradient of the potential, and that expression can be converted to total divergence by virtue of the fact that the divergence of the current density is zero in a steady state, and we're of course only considering the steady state situation. And therefore, the rate of production of heat, as manifested by the power being exerted on the electrons which carry the current, is given by this surface integral, right? Because one can use the Gauss theorem to convert the bulk integral of the divergence to the surface integral without the divergence. And the consequence would be this expression over here. Okay, so now imagine the surface to be this a cylindrical surface, and the whole thing is a manifestation of a current carrying wire, and the two end surfaces are denoted as S1 and S2, and the current will flow obviously down the cylinder. And this surface integral after some reflection will be equal to the current. The current basically comes from performing the surface integral of this inner product, which is nothing but the definition of the current in the first place. And there are two surfaces that are at different potentials. So you have the current multiplied by the potential difference. And this potential difference is nothing but the voltage. So all in all, the rate of production of heat turns out to be equal to the current multiplied by the voltage, which also equals the current squared multiplied by the resistance once you invoke the Ohm's law in the circuit version, namely V equal to I times R. Okay, so you have probably seen this result many times over in your previous education, and what I've done is probably a slightly more sophisticated version over the previous derivations you may have seen. But of course, the final expression is not changed from what you learned earlier. Okay, so thank you.